vamos a tener la charla de Chris Morgan, un investigador docente de la Universidad de Nevada en Reno, que desde hace ya varios años, diría casi 10, que está trabajando y colaborando con nuestro departamento. Hemos podido ir al campo juntos, hacer algunas publicaciones también. Y él ha sido alumno de Robert Bettinger, donde se doctoró en la Universidad de California, Davis, a través de lo cual él se inició en los estudios de cazadores-recolectores de altura, especialmente en lo que se denominó en su momento las aldeas de altura, en las montañas blancas de California. Y hoy va a presentar un trabajo realmente que para nosotros es sumamente interesante, con materiales de acá del sur de la provincia de Mendoza, discutiendo la funcionalidad y el tipo de ocupación que se da en estos sitios ubicados a más de 3.000 metros de altura en el sur de la provincia de Mendoza. Así que, bueno, con ustedes, Chris Morgan, el doctor Chris Morgan, esperemos que disfruten la charla.
Muchas gracias, Gustavo. Lo siento, no hablo muy bien español y necesito hablar inglés. Gracias por su paciencia. I will probably speak terrible Spanglish also for the next 40 minutes, so I will try. So again, most of you were here last week on Wednesday, so thank you for coming again, and thank you, Clara, for setting this up, and Gustavo, and all of you for having me. It's really been a wonderful trip, so I'm really honored to be here and have the opportunity to talk to you about your own archaeology. So I'm a little bit embarrassed. I'm a little bit, I'm not trying to tell you how to interpret your archaeology in Argentina, but what I want to do today is talk a little bit about using a model derived from behavioral ecology, and that is the Z-score model, which is a kind of uncommon model. We're used to the diet breadth model, right, the prey choice model. Well, this is a different model. I think it might be I think it's a useful model to use and to think about when trying to model environments and ecological settings that are risky or very uncertain in terms of how people might occupy them. And those situations pertain especially in high altitude settings. So what I want to talk about today is why live at 3,300 meters elevation. Risk seeking and risk mitigation in the high Andes. So I'll start off this talk with a little bit of, and I know some of you have seen this, or even played, this is a film put together by Camera Documental, the drone imagery operators, back in 2019. And the imagery is just fantastic. I know a lot of you have seen this, a lot of you were actually there. And it shows the way that the houses are constructed at El Indigeno. It shows you some of our excavations, both in the houses and in the middens. This is just below the crest between Argentina and Chile. You can see the houses are grouped together in clusters, sometimes almost like apartment blocks. And excavations have gone on there since La Higlia back in the 1970s. And you can see that the excavations produced a wonderful set of artifacts, and there are over 200 houses, or habitaciones, structuras, on the landform. There's over 130 structuras in the site itself. It's at over 3,300 meters elevation, and this final image really shows the layout of the core area of the site. So this is a really big archaeological site, indicating probably a lot of people lived up here during a period of time, starting around 2,000 years ago. And then the question then is why would people live at this archaeological site? Well, I think this question can be partially answered by thinking about how and why and where and when hunter-gatherers in particular started living in high elevation settings. And this map The yellow parts show the areas where hunter-gatherers intensively occupied high elevation settings. The first here is where I started my work. The Sierra Nevada of California. This is where I wrote my dissertation now over 20 years ago. And the Rocky Mountains of the western United States, where I've worked, especially in Wyoming and Utah, looking at high altitude village sites there. More recently, I've become involved. I've worked in China for over 25 years, looking at the Lus Plateau, which is a lower elevation plateau, about 1,500 meters elevation. But in the last decade or so, I've been working with a group of scholars in Beijing on trying to understand hunter-gatherer occupation of the Tibetan Plateau, which is very, very high, sites as high as 4,300 meters, going back in time to 30,000 years ago. Very, very old, high elevation sites here in Tibet. I have been to the Alps, but I've never worked in the Alps, and I've never been to the Ethiopian highlands, and I hope to get there before I die. But here we are, of course, in the Andes of South America, and it is the long altitude human adaptations. So all of these settings have some environmental characteristics in common, and the first is low biotic productivity. This map is a map of net primary productivity. It's just NPP. It's just a measure of how much of the sun's energy turns into plant biomass. And you can see here, this is the Wind River Range, and the light colors are lower environmental productivity. And you can see the lowest environmental productivity is here on the highest elevations of the Wind River Range. And this is what it looks like during the summer in El Verano. A little bit of grass, mostly broken rocks, and this is the remnants of a rock glacier, a very small glacier that formed here at the end of the Pleistocene. Generally low biotic productivity at high altitude. Also pronounced seasonality. This picture was taken just 1 month, un mes apart. This is in Mayo 2012. I went up because this was the only place to get cell phone coverage. As a student, we were excavating this site, and I had to climb up to the top of the mountain to call for help. And I took this photograph, and just less than 1 month later, so it was only 2 semanas, 2 weeks later, you can see that even though the grassland is pretty well cropped, these are mountain sheep, Ovis canadensis. And you can see that the biotic productivity is in the animal biomass here. So a lot of calories in these large-bodied mammals. Another thing that characterizes high-altitude environments is, of course, less oxygen. Oxygen drops almost in a linear pattern to the point that compared to sea level, at 3,000 meters, there's almost only half as much oxygen at 3,000 meters as there is at sea level 3,000 meters lower. And this results in humans only being able to get the oxygen and put it into their body and put it into their bloodstream at a marginally declining rate. And it really becomes a problem around 2,000 meters elevation. So if you go up to 2,000 meters, that's about 6,000 feet elevation. You start to breathe harder, and this is because your body just is not adapted to getting the oxygen out of the atmosphere at reduced concentrations. The effect of reduced oxygen is higher caloric requirements. It takes more energy to work at altitude. For those of you that remember working at El Indígena, you have to eat a lot when you're up there just to work even a little bit. And this really shows that this is a study of women runners at high altitude. And you can see here that normal caloric requirements are around 2,000 kilocalories per day for these are women, but human beings in general at sea level. But at high altitude, especially above 3,000 meters, caloric requirements are 30% or 25% greater than they are at sea level. That means individuals on average need another 500 or 600 kilocalories per day just to do the work that they would normally do at sea level. And of course that means they have to eat more. So the question then is why live at altitude? It's It's oxygen deprived, there's very little oxygen. It's oftentimes cold, of course. It requires more energy every day just to live a normal life. There's only a brief period each summer, usually a month, 2 months, sometimes 3 months, where the environment is productive enough to really encourage human occupation. Oftentimes resources, plants, animals, and even water are in very short supply, so a very challenging environment. And critically, due largely to the unpredictability of the weather, the unpredictability of animal migration patterns, and rapid changes in climate and weather. It's very unpredictable, it's very risky to live at high altitudes. And the question then is why live at high altitudes, and how do we model the risk? Well, to understand that, we need to go out and excavate sites. So this is the public part of the talk, and I just want to show a few slides that shows how difficult it is to get up to El Indígena and to work there. For those of you, several people here were up there. And you're all looking a little bit grayer since 7 years ago, but this is what it looks like. There are 136 structures at the site, over 200, apparently more now, on the landform as a whole, and the main occupations of the site were around 1,500 to around 500 years ago. This is what it took to get up there. This is, I just took this video the other day on the road up the Rio Altitude day, but interesting to wake up to this one morning. This is us during the snowstorm in the tent. You can see we have our resident, I don't remember the dog's name, but it's a very, very nice dog. Indy, right, and you can see, whoops, we're all wrapped up in all the clothes that we have, because it's very, very cold and snowing, and we're under this small tarp with the fire going. Of course, we did end up excavating the site. There's Fito excavating a 1 by 1 meter excavation unit in the midden. There's my student Dave Harvey, now Dr. Harvey, helping excavate at one of the houses. This is Hector, I think this is the video. Yes, you can see him excavating this pot, carefully excavating this pot. And so really nice preservation at the site. Rare to see a pot left upside down like this. People clearly intended to come back and use this pot. And there's Gustavo after the pot was removed. You know, so Gustavo has lost his hat at this point. And this is coming back from the site. This is my favorite part, my favorite video. Again, Gustavo took this. I was very scared at this point. Getting down this trail, there's really no trail, it's all just rocks. The horses are very sure-footed. The Puesteros seem fairly confident. But you can see this was, I learned to pray in Spanish while we were coming down here. And this is what we looked like at the end of that trip. And I love this photograph, because this is, once we got down to the mountain, we're back at Laguna del Atuel. We have one more day to ride the horses out to the cars, but we were all exhausted by this point. And the best part of this is, even the Puestero looks very tired and exhausted after this hike. So it's very difficult to get to the site, it's very difficult to work at the site, and it's very difficult to get home. And so this brings up the question, is why live at altitude when it's really so difficult, even for us with our modern technology? We have horses, we have Gore-Tex, we have down jackets, we brought all our food, we had canned food, we had wine, vino, I brought whiskey, we had all the important things to live at altitude. I think we were up there for 10 days or so. And by the time we got down, we were all, maybe I only speak for me, I was very, very tired and very, very happy. Even though I had a wonderful time up there, I was very, very happy to be home. Well, there is a way to model risk and uncertainty, and it is a different model than the diet, breadth, or prey choice model that a lot of us use when applying behavioral ecological models to predicting and explaining human behavior. And Carol Boland, who you may be familiar with, she was a student of Bruce Winterhalter's, and she was interested in, and still is interested in, how hunter-gatherers and why hunter-gatherers switch from hunting and gathering to agriculture. And she says that a foraging decision has, yes, I can. You want to be able to read it, so you're not going. So a foraging decision, what type of food you choose to eat, has a mean reward it has an average reward, and then a range of expectations of rewards around that mean. So if you think about a normal distribution, there's the middle, right, and that's the mean, but then there's a range. Sometimes you'll get less for deciding to eat that resource, and sometimes you'll get more. And so what Carol Golan recognized is we can model what the mean is and what the range is using a very, very simple model. And that model is called the Z-score model. And the Z-score model, who's taken a class in statistics? Okay, we all need to take more statistics. So the Z-score is a very simple model that takes a range of observations, generates a mean and a range, and then a standard deviation, and standardizes all of those numbers to 0. So 0 is right in the middle, and there's a range around 0. So you'll see how important and how easy this is to use the Z-score model with resources that are used, you can't see again, by hunter-gatherers. All you have to do is generate R-min, which is the minimum caloric requirements to get through a day, a year, a month, typically a day. So this is called, in ecological terms, the minimum level of subsistence, which you may have heard of, or NLS, but Winterhalter, who published this model, calls it R-min. So this is the minimum number of calories you need to get through a day, typically for humans, although it varies, around 2,000 kilocalories per day. At sea level, about 2,500 or 2,600 kilocalories per day at 3,300 meters elevation. U is simply the mean, the average return rate, el medio, for whatever resources the hunter-gatherer might want to eat. Maybe it's guanaco, maybe it's an armadillo, maybe it is a huevo de reyes, see? And so this is the mean for large body animals, lots of kilocalories per hour. For guanaco, it's around 14,400 kilocalories per hour. But of course, there's a range about that 14,400 kilocalories per hour. And that range is standardized to a standard deviation. And the standard deviation is just the average deviation about that mean. So if we have these numbers, we know how many calories it takes a human to live every day. We know what the average return rate is for a resource. And if we have a pretty good understanding of the range, the standard deviation of that resource, then we can use the Z-score model. So as an example, everyone likes steak, carne, right? The return rate for a steak is around 700 to 900. These are real numbers, 700 to 900 kilocalories per hour. Doesn't take very long to prepare a steak. Only a few minutes to put some salt and pepper on it. Some Americans put too much on the steak. Here, just a little salt and pepper will be fine. And then, depending on how pink you like your steak, how well done, maybe 15 minutes, maybe less if you like it very rare, like a North American, maybe a little bit longer in Argentina. So only 20 minutes, so that's the 20 minutes divided into 800 kilocalories. The return rate is around 40 kilocalories per minute. I've kind of generalized what the standard deviation would be here based on this range, around 50 kilocalories per hour. So 2,400 kilocalories per hour, that's a pretty good return rate. And we have to eat our salad, yes, la ensalada. Very low return rates, of course, only around 200 kilocalories per hour. It doesn't take any time at all to make a salad, just chop some lettuce, throw it in the bowl, you're ready to go. 200 kilocalories per hour, about 10 minutes to make the salad, a smaller standard deviation. That's around 20 kilocalories per minute, or around 1,200 kilocalories per hour. Half the steak, in other words. So plant foods, very low return rates. Animal foods, high return rates. Typically animal foods with a higher standard deviation, simply because animals come in very different sizes. If they're a small guanaco, they're a very big guanaco, and sometimes there are medium-sized guanaco. So, it's good so far. Z-score model. Okay. Critically, what I'm showing you here does not include search time. So if we think about this, the search time for a steak or a salad is you get in the car and you drive to the supermercado and you buy it and you drive it home. That would be equivalent to search time for a hunter-gatherer. I'm just saying this now to put it in your head. Remember, we have to come back and think about search time. And search time is predicated, it is dependent upon the frequency of those resources in the environment as a whole, how much time it takes to find whatever resource a hunter-gatherer might be looking for in their environment. Does not include search time. We'll talk about it again in about 15 minutes. Okay, as an example of how the z-score model works, so remember, we've got our minimum level of subsistence, our min, we have the average return rate for a resource, and we have the standard deviation of that resource. We know at sea level that it takes around 2,000 kilocalories per day to stay healthy and reproduce. Let's pretend we are going after a resource, we are pursuing a resource that has a return rate of 3,000 kilocalories per day, kind of an average return rate, and a fairly large standard deviation of 1,000 kilocalories for whatever that resource is. And the reason I'm using these numbers is just so the math works very, very easy. So you can do the math very easy. 2,000 minus 3,000 is negative 1,000 divided by 1,000. Whoops. Divided by 1,000 is negative 1. So the z-score is negative 1. Very, very easy. Right? Negative 1 is good because it stands for negative 1 standard deviations. And for those of you that have taken statistics, it is based on estimating the amount of area under this. And this is called the normal curve. The middle part here is the mean, el medio, and you can see here the number of standard deviations. 1, 2, 3, 1, 2, 3, to the right, so these are positive standard deviations, and to the left are negative standard deviations, 1, 2, 3. So if we get a z-score of negative 1, that is right here. So we want negative z-scores if we want to be less risky. Because what this means is that there is everything left to the left, a la izquierda, of this line is the probability that you do not meet our min, that you do not meet the minimum level of subsistence. To the right, al derecho, this area under the normal curve is the probability that you will or you will exceed the number of calories you need to get to meet the minimum level of subsistence. So all this depicts are probabilities, the area under the normal curve. Okay, that's all the statistics I'm going to talk about. I promise, because there's an easier way to think about the area under the normal curve, and it looks like this. Muy fácil. With a z-score of negative 1, there's an 85% probability that you will meet the minimum level of subsistence, and a 15% probability that you will not meet the minimum level of subsistence. So is this a risky strategy? 85% chance that you will succeed. No, it's very, this is really, I live in Reno, Nevada, where we gamble, right? And so I teach my students this, and you say, if you have an 85% chance of winning, you always take that bet. This is a very, very good, a very safe bet. This is not a risky strategy. Uh-oh. What happens when we increase the minimum level of subsistence, the number of calories we need to get through a day? This might occur, and we know this occurs at high altitude, right? It takes 500 calories per day, but it also might occur if, who has babies? I don't have babies. So you have children, right? And do they work? That's a joke. A parent has to get the calories for themselves, and they have to get the calories for their child. So you could easily double the number of calories that you need to get every day if you are foraging for another individual who can't forage for themselves. It might be a child, it might be a grandfather, an abuelo, right? And so we can imagine a situation where the same resource, 3,000 kilocalories plus or minus 1,000 kilocalories per day, we need to double the amount of calories we get. you can see the numbers come out very easy. 1,000 divided by 1,000 is 1. We have a z-score of 1, and that just inverts what we saw before. A 15% probability of meeting how many calories we need, and an 85% probability of not getting enough calories for that day. Again, easier way to think about the area under the normal curve is just with a pie chart, a round chart like this. 85% bad, 15% good. Is this a risky strategy? This is very risky. 85% chance of losing, of not getting enough calories to live. And if you kept on making this bet day after day after day, you would probably starve to death unless you got really, really lucky. Okay, one last slide. I lied. A little bit more statistics. So what happens when z is closer to 0? And 0 means 50% one way and 50% another way. So if z equals negative 0.1, what that means is that you have a 51% chance of succeeding and a 49% chance of not succeeding. And now the question might get a little harder, or maybe it's not. So let me ask you, those of you that don't live in Las Vegas or Reno, is this a risky bet? No, why not?
Because maybe you don't have another choice, and you have 50% of possibility of survival.
Okay, that could be true. That could be true here too.
No, because there you have less possibilities to get your needs.
Okay.
And in the other one you have more possibilities, so it's not risky.
It's not as risky as the last one.
It's more neutral.
It is absolutely a lot less risky than this. So if those are your two alternatives, you're of course going to do this. But I'll tell you this, and there are gambling problems at the university, so I teach my students to gamble. It's maybe not the best strategy. But anyone who bets on sports, the World Cup, you bet that Argentina will win and Venezuela will lose. Hopefully, yes. The US will definitely lose. Is if you can get your probability just above 50%, you always take that bet. Every good gambler knows this. The casinos in Las Vegas know this too. They have a 51% chance of winning. You have a 49% chance of losing. And that's all they need to make tons of money. Because how many times do you gamble in Las Vegas? You know, to illustrate 100. You might play 100 hands of poker. And if you play 100 hands of poker, you're going to lose 49% of the time. And the casino is going to win 51% of the time. So this is a good bet. If you can get above 50%, on average, you're going to win. And that is a very, very good bet. You always take 51%. And what that means is if z-score is ever positive at 0.1, this is a bad bet. Once you get below around 50%, this becomes a very, very risky bet indeed. Okay? With me? Okay. I don't know if I'm with you. Okay, so now we need to estimate what if we want to apply the z-score model to places like El Indigeno, we need to think about what the caloric requirements are for different population sizes. So here we have, Gustavo tells me this is a bad word, but it's the proper word in anthropology, hogares, and this means, of course, households. Not casas, not estructuras. These are households of people, usually comprised of maybe 4 people, 4 personas, a man, a woman, a child, maybe another child. So you can think there's, in 3 casas, or 3 households, there's about 12 people. We can just multiply that by 2,500 kilocalories per day. That turns into 30,000 kilocalories, which means our minimum return rate has to be divided by 8 hours in a day, 3,750 kilocalories. So we do this for each population size, 3 households, 10 households, or there are 200 houses or more at El Indigeno. Just to model this in the extreme, 200 houses, which require 2 million calories per day to support that population. So here we have, very easy to generate our min for a population for different population sizes. So right away we have 1/3 of the data we need to apply the Z-score model to high altitude living in the Andes. Now the question then is what are the mean and standard deviation of return rates for different animals and plants that are found in the southern Andes? And the southern Andes are very interesting to me. I started coming here in 2013, and there is not a lot of vegetation in the southern Andes. There are very few animals. This is a very resource-deprived region compared to places further north in Peru, or certainly in North America. So the animals that people can eat mostly consist of these, of course, guanaco, some armadillo, a little bit lower elevation, and then Gustavo has been very kind to me to show me all the plants that are available. Very small seeded shrubs, small fruited shrubs, some cactuses with, of course, very, very low return rates. And fortunately, I used to have to cheat and use North American return rates, but fortunately, in 2022, Corbett et al. Published the return rates for Alto-Andean fauna and flora. And the ones I want to talk about are these. Are the foraging return rates for the types of plants that might be available in or near El Indigeno. You can see very, very low return rates here, around 500 to 600 kilocalories per hour. These are very, very low return rates. Terrible return rates. Terrible return rates in North America are 800 to 1,000 kilocalories per hour, double this. So compare that, of course, to hunting. And the only animal that's really available up at high altitude is the guanaco, and really nice return rates there, over 14,000 kilocalories per hour. Unfortunately, the standard deviation of these return rates are not available in this publication as far as I can tell, so I estimated the standard deviation based on the standard deviation for comparable fauna and flora in North America. So here you can see we generate the mean and standard deviation for simply foraging. You can see a very low return rate, less than 600 kilocalories per hour, a fairly small standard deviation. We can multiply that out to a day if you want to. For just hunting, of course, this is the return rate for guanaco, and we multiply that by 8 for hunting for an entire day. And then a mix, 50% foraging and hunting. The math is a little bit funny here, around 5,000 kilocalories per hour. Plus or minus 2,000 kilocalories per hour for a mix of foraging and hunting. So a very simple model. Now we have our min, we have the daily minimum caloric requirements for a group, for a population. We have the mean return rate, and we have an estimate of the standard deviation. Now we can use the Z-score model to figure out just how risky it would be to live at El Indigeno and other Alto-Andean sites. Oh, and there they are. There are the Z-scores. I checked my math last night and it was wrong, and I fixed all these very late at night last night. These are right. I don't know what happened. Anyway, so these are the Z-scores for just foraging, just being a hunter, just being a gatherer, just for hunting, and again the mix here. And right away, when you see negative numbers, you know this is good. This means there's a high probability of meeting minimum level of subsistence. When you see big positive numbers, that means it's really, really bad. So Z-scores, especially for people that hate statistics, and I don't know anyone, I like statistics, but deep down I hate statistics. We can turn these into probabilities, and the probabilities make it very, very understandable. This is the probability of success. These, of course, all approach 100%. Of course, these all approach 0%. So we can map this out, and I want to just look at this at 3 different population sizes. 3 households, 10 households, and we'll skip over all these, but we could do it for the other ones too, and 200 households, the maximum number of households one might expect at El Indigeno. This is what the probability of success looks like for 3 households or 12 personas, 12 people. Very high probability of success. And so this is not a risky settlement strategy during the summer for very, very small hunter-gatherer populations. And this is not surprising, right? When we go up to the high mountains, I've worked in the Wind River Range, I've worked in the Rockies, I've worked in mountains in Nevada, I've worked in the Sierra Nevada, I've worked right next to the Tibetan Plateau, and we find small hunter-gatherer sites everywhere, indicating very small temporary populations. So not surprising, because it's not a very risky thing to bring a few people up to the mountains for a few days. It changes with only 10 households, and this is only about 40 people, 40 personas. is right away, because of the very low return rates of alto-andina plants, it becomes very, very risky once populations reach 30 or 40 individuals. Hunting is still a very non-risky strategy, and foraging and hunting is still not a risky strategy. The extreme, of course, is with 200 houses. And at 200 houses, this is always a bad bet. It's always very risky. You will almost certainly fail to provide enough calories for a very large population. With foraging and hunting, you will almost certainly fail as well. And if you just hunt, you have about a little less than a 50% chance. If you're just hunting, you still could fail more than half the time, meaning this is a risky strategy too. This graphs out the previous data. So what this shows is that around 7 households, 7 families, it becomes risky to occupy altitude. This is where the line intersects 50%, that z-score of 0. For hunting, it's around 190 houses. You think, well, that's a lot of houses. Maybe that's just what people were doing up there. They were hunting, and they were a hunting-focused society, and it would support very large populations. Maybe, we'll get to that. And the last one, a mix of foraging and hunting, it supports around 40 households. And you think, well, that would work pretty well too, right? It's 40 households, it's a lot of households, and maybe that's the solution, is to have this mix of foraging and hunting. Well, the problem with this is search time. So this graph shows you the minimum number. So if you look at this, the answer to this is Wanako. If you hunt Wanako, maybe you can have lots of people up there. But then the question then is how many Wanako do you need to capture every day to support populations, 12 people or 600 people? Well, for a population of 3 households, you need to capture less than 1 Wanako a day. Do you think you could do that? Do you think this is probable? Probably, maybe half the time. For 10, do you think a population of maybe 30 or 40 people could capture 2 Wanako every day? Maybe. Do you think a population of 200 households could capture 42 Wanako per day? No. It's impossible. The Wanako would be wiped out. Well, first, it couldn't happen. And second, if you did kill all those Wanako, there would be no Wanako left for the next day, right? So this means that we have to think about what is the effect of search time on the z-score. Well, I've struggled quite a bit with thinking about how to model search time. And there are obviously more realistic ways of modeling the probability, the likelihood that a hunter will, 1, encounter a Wanako while he is out hunting, and 2, that he will successfully capture that Wanako. And I'm working with a student of mine right now to create a computer program that is much more realistic than the numbers I'm going to show you. But this math is very, very easy, and I think it holds up. I think even though it's a very simple model, it's a good way of thinking about the effects of search time and the probability of hunting success with very, very simple math. So the question then is what is the probability? What is the chance that a hunter will both find a Wanako and capture that Wanako, kill the Wanako? Well, that's probability number 1. That is an independent variable. And then the other probability is, what is the probability that that Wanako will meet our min? That is the probability of B. So B is dependent on A. Here. So this is an independent variable, this is a dependent variable. And if you're so interested in the math, this is what it looks like. It's fun doing math so that you will get angry at me. All this means is, what is the probability of A occurring and then B occurring? Well, the answer is, it's just the probability of A multiplied by the probability of B. The math is very, very simple. It's just multiplying that by that. Well, worldwide, and the data are quite variable, but on average, hunter-gatherers have a hunting success rate of around 30%. So I'm going to use that 30% to stand in for the probability of identifying, encountering, and capturing prey. So this stands in really for the animal abundance on the landscape. And then meeting our min is if you capture that, then that's 100%. So it's very simple. It's just multiplying 30 by 100, and of course the probability turns into 30% rather than 100%. So if you generate the z-scores, and I generate the z-scores, but here are the probabilities associated with the z-scores once we factor in the probability of hunting success. And you can see, of course, especially for hunting, the first ones drop to 30%. That's just because of the simple math of a 30% probability of hunting success. So once again, if we look at 3 households, Diaz households, 200 households, what do those pie charts look like? And that really tells us the story. For 3 households, again, foraging works pretty well for 3 households. Hunting doesn't work so well because it's very unlikely to capture that many guanaco every day. You notice the percentages are a little bit better here for foraging and hunting. I think the important thing here is relying on plants, even with small population sizes, is a little less risky than hunting alone, even with very small population sizes. With 10 households, of course, foraging, because of the very low return rates, becomes very, very risky, as we saw before when we did not include search time. And again, when we add foraging and hunting together, actually that becomes a not so risky strategy. This is a pretty good strategy for 10 households, maybe 40%, 40%. Of course, there's really no solution for 200 houses. It's always very, very risky to live with this large a population at El Indigeno for any amount of time. There's only a very small percentage probability of succeeding when we only subsist on guanaco. So, take-home message, very, very risky at all levels except the smallest levels of population. This graph spells it out again. No surprise, here is the transition from a 50%, greater than 50% probability of success occurs when we're just foraging at around 7 households, just like we saw before. This is the hunting line, this is Casa. There is no solution here. It is always risky. It is always, you always have less than a 50% chance of succeeding when you only hunt. The last one, this is the interesting one, is when you forage and hunt, it looks like the transition to a risky strategy occurs around 25 households. So if we had to make a prediction as to how many households would have been occupied at El Indigeno at any one time, maybe around 25 houses, based on the model. We don't know if this is true or not. And the more interesting part of this exercise, this mathematical exercise, is whether you're above or below 50% probability of success, is that it is less risky to hunt and gather than to just hunt below around 40 households. So I think the really important part of this model is that this solution set here between around 20 and 40 houses, this is the area where you don't only have to hunt and take a very risky bet to support these large populations. Okay, that's the model. I promise I won't talk about the math anymore, but I think this is a really interesting way, the z-score model is a really interesting way of thinking about probability of hunting success and the probability of meeting caloric requirements in ways that the diet breadth or prey choice model does not cope with, especially in environments that are hard to live at, like hands. So the question then is what do the data tell us about whether our model is right or whether our model is wrong? And what do the data imply, given this model, about why people would live at such high altitude? Given how risky it is, the model will show that it's almost always a bad idea to live at altitude. So what do the pots tell us? What do the pot shirts tell us? What does the groundstone, the monos, and the tates tell us? And what do the projectile points, components, and macrobotanicals specimens tell us? Well, I will look at the data. Of course, you all generated most of these data, so thank you for that. I'm going to look at 3 sites, Risco de los Indios, El Indigeno, and the sites around Luna del Diamante. And all these data are derived from a book chapter Gustavo and I put together a few years ago. So of course, Laguna del Diamante, hopefully we'll see it soon. Risco de los Indios, this is where I first became involved with working with you all in 2013. El Loco was excavated in structure 22, and of course, El Indigeno. What do the data from these sites tell us? Well, this is a bar chart of the percentage of different artifact types from these three main high altitude sites. And I just want to draw your attention to a few things here. First off, there's a lot of ceramics, and in fact, El Indigeno has a high proportion of ceramics, and those ceramics come from Argentine sites and from Chilean sites. They come from both sides of the Andes, apparently, but I'm no expert on that. There's groundstone at most of these sites, and El Indigeno has the most groundstone. Groundstone, of course, would indicate processing plant foods. Maybe foods brought from lowlands, maybe foods collected in the vicinity of the site. Importantly, projectile points, almost none. There were a fair amount of projectile points at Risco de los Indios, but compared to the volume of sediments excavated from these sites, there are almost no projectile points. And you compare this, my mentor, Robert Bettinger, I noticed you mentioned Bettinger at the start of this. In the White Mountains of California, there are thousands of projectile points at these sites, indicating that hunting was a focus there. If we just look at the projectile points, this would seem to imply that hunting was not a focus at these sites. Another thing that's kind of interesting, Risco de los Indios had a lot of pigment, but Risco de los Indios is a much later site, only about 500 years old. So, take-home message, the most important part is there's about a moderate amount of groundstone, there's a lot of ceramics from different sources, and almost no projectile points. What does the faunal remains tell us? That is my hand. So these are the archaeofaunas from these sites, and you can see while there are the occasional birds and armadillo or armadillo here is the most important thing, is there's a lot of guanaco bone proportionally at these sites. And in fact, Risco de los Indios has quite a fair amount of guanaco remains, but the Laguna del Diamante and El Indigeno sites have all comparable amounts. So when you present the data like this as a percentage, it looks like there's a lot of animal bone, especially guanaco bone at these sites. The critical part of it is the density of bone is fairly low for most of these sites. For the amount of dirt that was excavated and poured out of the screen, the actual minimum number of individuals, the NISP, are comparably low, especially compared to North American sites where hunting appeared to be a focus. So did people hunt guanaco and eat guanaco here? Of course they did. Did they eat a lot of them? Probably not. There's just not that much bone at these sites. Surprisingly little bone at these sites. What do the macrobotanical remains tell us? This is Gustavo's specialty. I hope I get it right. Here are the macrobotanical remains from, I can't remember if this is El Indigeno. These are the data. And the data are interesting is the diversity of faunal remains. You can see there's very little overlap in different sites. They all have very different macrobotanical signatures, but I would just want to draw your attention to just a couple things. The first off is there is evidence of eating wild plant foods at all of these sites. Not a lot of evidence, but definitely people were eating wild plant foods. And this is consistent with the metates that are found, and the manos and metates that are found at these sites as well. But the more interesting thing is this. Phaseolus, squashes, and zea maize, which is, of course, corn, maize. And critically, these are domesticates. And this indicates, even though the sample sizes are very small, these indicate that domesticated plants were brought up to altitude. And we would argue that this is a way of mitigating risk. When you get up to altitude, bringing some food with you is a way of ensuring you have enough calories to at least live for a few days before you need to capture a guanaco. So we see this pattern in North America as well. In Utah, you see maize at very high elevation. In hunter-gatherer societies like I would see, you see acorn elotes brought up to very high elevation to mitigate the risk of living at high altitude. Okay, so to summarize this, I would argue, and I hope you would agree with me, that hunting is almost certainly important. There are guanaco remains at all of these sites, and there are a few projectile points, but it's probably not the focal economic activity. It is not the main thing people do to subsist at high elevation, so it's not the reason they're up there. They're not up there specifically to hunt Monaco. There is evidence, especially with the groundstone. I'm interested to see what the macrobotanical means when those data are available. There is evidence of intensification of eating wild plants and domestic plants as well. So that's a big part of the picture. It's a way of mitigating risk is to rely on lower ranked plant resources. As I said before, bringing domesticated plants up into high altitudes is a way of mitigating some of the risk of living at high altitude, but again, those sample sizes are fairly small. There is an abundance, especially at El Indigeno, of Chilean and Argentine ceramics showing that the site was probably an important node in interactions between people to the west and people to the east of the Andes. Las Cargas Pass is only 6 kilometers away from El Indigeno at 3,500 meters, so this proximity to the pass may have something to do with why El Indigeno is what it is. Of course, one of the reasons that it's one of the only places with good water in the entire area up there. And finally, I'm going to end with this idea is people don't go to El Indigeno or these other sites specifically to hunt Monaco. They don't go to these sites specifically to collect wild plants. They go up to these sites probably to trade. And if people are trading with groups on either side of the Andes, they're probably doing other things as well. One of the most important things I think that people do when they engage in trade relationships is they find mates. This is an important way of getting a wife, getting a husband, maybe more than one wife, maybe more than one husband, during these trading expeditions. And the other part of trading interactions is just sharing information. What's going on in, we didn't call it Chile then, but what's going on in Chile? What's going on in Argentina? Where are the good plants? Who's getting along with each other? This importance of economic exchange, mate exchange, information exchange, and perhaps the prestige and the status that goes with knowing this stuff. The information that one gathers from going up to the high altitudes to get information, to get mates, to get economic goods and pots. So what I want to argue here is that living at altitude is really costly. It costs 1.3 times the calories of living at low elevation. It's really risky to live at altitude with groups that are more than maybe 3 or 4 families, 3 or 4 hogares. It is to generate large village sites like El Indigeno. The only way that a group could support itself would be to intensify wild plant foods and to bring up domesticates or other wild plant foods from the lowlands. So that's a way of mitigating some of the risk of living at high altitude. So the critical part of this is that why do people live at high altitude? Well, the connections to the lowland patterns, the farming patterns, and the intensive hunting gathering patterns in the lowlands ends up being critical. And then the question is even if you intensify wild plant foods, and even if you transport maize to high elevation, as the Z-score model indicates, it is very, very risky all the time to live at altitude. And for those of us that were at El Indigeno for 10 days know this. It could snow at any minute. The water could turn bad. The food could go bad. And then, or the animal or rodents could get into the food and eat your supplies, and you have no food to eat. So it's always very, very risky to live at altitude. And what this shows, I think, is that people are willing to live in a risky setting. They're willing to maybe starve. They're willing to do this for the social and economic and prestige benefits associated with mate exchange, with economic exchange, with information exchange, and with power exchange in this node between the west and the east of the Andes. And that's all I have for you. Thank you. Gracias.
In the model, how this kind of storage of domestic plants in the site, how introduce that that data in the model.
Yeah, that's a great question. I hadn't thought about that. That's a great question. So the question is, how would I take maize and beans,
Because that changed the
because that would change it. So the short answer was, you could do it. So here, I know how to do it. Well, I think I know how to do it. I mean,
Because in those sites, you have basically you have parcelos vulgaris and you have maize in the indigenous.
here, this is what. So here we have just foraging. This is for wild plants. And this is just hunting of wild animals. And this is foraging and collecting wild animals and wild plants. You could make another column and now I have to do it, or someone has to do it. It's to add, to see what the risk would be with different amounts of beans and corn in the diet. It would be easy to model.
The same process that with the data of that plant.
So then the question then is it one of the things that's hard? It's just a model, right? And so the model is, I think, if I remember right, this is 50% foraging and 50% hunting. Well, then the question is, foraging, collecting, and domestics, what are the percentages? And we have the return rates, but then the question is, you just have to put the numbers in and make a model. But it's a really good idea, we should do that.
And include the transport cost from
Right. Like a central place model, yeah, exactly. Yeah. It's one of those things with models, is when they are very simple, they are more wrong, but they're very easy to do. And the more realistic you make a model and add more realism and detail to a model, they're better, they're more accurate and they're more precise, but then they're very, very hard to understand. And so this is where we always are with using behavioral ecology models. Is the diet breadth model is a stupid model. It's just a simple, stupid model, but it has very high predictive power. And the question is, how much realism do we want to add to this model? So one, I don't get confused, because I will, and the people that read the paper, we don't want them getting confused as well.
I ask you that because we try with isotopes in organic residues, and it's a difference between the ceramics that are from the highland sites that have very low nitrogen and carbon that are associated with the wild plants, against the Piedmont sites that have a lot of nitrogen and lower carbon, but a lot of nitrogen. So it's a difference that is very related what you say, that the ceramics is related with the white plants, especially. And I don't know with the poroto, that maybe have the same values, but it's related with the white plants, especially in these sites. So the process in the ceramics is related, especially with the plants, not so much with animals. For example.
Have people been successful getting the residue off the pottery, or
I made isotopes.
Or even just the residue, the starch grains?
Yeah.
No hay inicios de residuos.
No.
Solo isótopos, no líquidos.
Sí, solo only
Just the
from the residues.
It would be an interesting project to do.
Yeah. We have one candidate.
Si el lugar hubiese sido utilizado como una trampa natural de guanaco, ¿no cambiarían estos números? ¿Y una caza masiva de guanaco?
He wanted to know if the number change, if you think the place like a natural trap to hunt guanacos, where you can hunt in greater numbers the guanacos.
Right, so as Mile knows, as well as any of us, better than us, that El Indigeno is a special place, and it is the only place with water. There's the stream from the glacier that runs by the site. The water is not very good, but it's water. And then there's the Vega, adjacent to the site, and no doubt birds are attracted to that, although there aren't that many bird remains from the site, which is interesting. And Guanaco would be attracted to that as well. They need the water, they need the grass. It's the only place where there's high environmental productivity. And this is true wherever I've worked in the mountains, is if there's a spring, a vega, that's where the site is. And that's true here, it's true in North America as well. So would more of Guanaco be around El Niño? Yes, because there's water and there's plants to eat. But once people are there, do the Guanaco want to live there? No. So the poor Guanaco, we could model the Guanaco behavior too, when people do this, is how risky do the Guanaco want to be? They need the water, they need the plants, but if they go there, they might be killed. And so that is the model that I'm trying to work on with my student, is putting different populations of Guanaco, 100 Guanaco, 50 Guanaco, putting them around the site, and then have people go in there and kill Guanaco. Every time you kill a Guanaco, one, they don't want to be near there anymore, and two, that's one less Guanaco, which reduces the probability of hunting success the next day that a hunter goes out. So we're creating a very complex model using an algorithm, a computer code, to hopefully be more realistic about prey behavior rather than just the human behavior. Does that make sense? Yeah. Okay. I am not so good at R, but students are good at R.
So thinking of the model, and that you said that the model shows that there is less risky if they hunt and gather. But in this case, in El Indígena, in our area, there is like very few vegetable wild plants. So is there a strong relationship, I think, between the appearance of agriculture down in the low elevation sites and the use of these risky areas?
I think so. So the question is, do people not start using these high altitudes
before farming appears? I am right?
Gustavo would know the answer to this better than me, but I have the data. I didn't put it in the talk.
Even though we have some wild plants, but it's not a lot.
This is the sum probability distribution from El Indígena, and you can see the site begins to be intensively occupied. Not a lot of radiocarbon dates around 1,200 years ago, and it stops being occupied at the Little Ice Age around 600 years ago. And all of the sites that we know so far, I don't know if they're new dates, these are kind of old data, but this shows the sum probability distribution of all of these sites. And even Laguna del Diamante, the occupation begins around when farming starts, around 2,000 years ago. So there is no evidence that I'm aware of people making villages in the mountains before farming.
And what did you see in other high elevation sites in White Mountains or in China? Is there this relationship or not?
Always very late. Well, there's no agriculture in the White Mountains, but there's very intensive hunting and gathering. In Utah, you don't see, whether it's the Fremont, you don't see people building villages in the Uinta Mountains until maize farming starts in the lowlands with the Fremont and Alabama. The interesting thing is if you go, I didn't know anything about Peruvian archaeology, and I'm still learning about Peruvian archaeology, but if you go north in the Andes, and it's much more productive up there as you get closer to the equator. And the equator, this talk is all about altitude, but latitude ends up being important as well. So as you get closer to the equator, high altitudes become better and better places. And it looks like people began intensively living at high altitude in the Peruvian and Ecuadorian Andes very, very early. Very, very early. Well, they started farming very, very early too. 6,000 to 8,000 years ago. Which just confuses me. I like the middle latitudes because it's easier. Any other questions? Well, thank you so much for having me. It's really been a pleasure and an honor. I really enjoyed being back down here and seeing you all again. And I hope to do it again in less than 7 years. How's that?
Thank you.
Yeah.